Good afternoon, everybody. So my name's Mair. I'm going to be talking to you about a small project we're doing in 5G today. So a little bit about me. I've been working in wireless for a few years, probably about 20-ish. And so the last few have been devoted mostly to 5G. And I work for a company called InQtel. So at a high level, InQtel is a nonprofit strategic investor that sources, funds, accelerates tech startup companies. Within InQtel, we have a subsidiary called IQT Labs, InQtel Labs. And what Labs does is, we look at open source material, academic research, along with some of our startup technology to see how we can demonstrate how we can solve some of our customers' problems. And within Labs, we have an engineering group, which I'm part of, and we build stuff. People say, "Oh, really? You build stuff? Interesting. Didn't know that." Yeah, we write code, we fabricate, we use startup technology where we can to build prototypes and demonstrate how we can actually solve some of our customers' problems. We're applied research, if you will. And so one of those is what I'm going to be talking to you about today. So this all started one day with a conversation. Hey, what would it take to disrupt a 5G, an all IP-based 5G network or 4.5G network? What would it take, just to cause problems and wreak havoc on one? And subsequently, how would we defend it? So we figured, okay, in order to do that, we have to build a 5G network or 4.5G network. And then we have to figure out what the attack surface looks like. How can you attack this thing? And then we have to figure out, okay, well, what's our defense strategy? How are we gonna protect this? So that's pretty much what we did. So you can see our Git repo up there. The internal project name is called Deadless. But yeah, you can pull that down. You can see what we did. We have we have all the source code in there and how to build it and instructions, readmes on how you can actually implement it. But I want to give a huge shout out to the rest of my team, engineering team, Charlie, Ryan, and Josh, who did and continue to do most of the heavy lifting. These guys are awesome. So just a little bit of 5G background. I'm not going to spend too much time on this, but just so we're on the same page. Any cellular network has three main parts, right? So you've got the RAN, the core, and the user equipment. So the RAN, that's the radio access piece where your handset talks to the radio and makes phone calls. Then you have the core network that takes data to and from the RAN and routes it and manages network resources, authenticates users, does billing, among other things. And then finally, you have the user equipment. These are things that use the network. So handsets, phones, IoT devices, vehicles in some cases. And a couple things that are not on here that we hear a lot are network architecture types. So you're going to hear two things called non-standalone, NSA, great acronym, and standalone, SA. So non-standalone networks generally use existing infrastructure. So you use what's out there to implement your 5G network. And there's advantages to doing that. One of them is being costs. You can kind of try before you buy, if you will. But you won't necessarily get all the things that 5G has to offer. The other type of network is called standalone, and that's building it from the ground up. And obviously you can take advantage of a lot more things, but it costs a lot more. So prior to 5G, 4.5G, a lot of these cellular networks had a lot of dedicated hardware and proprietary software running to make them work. And so this landscape has really changed with 5G. And these are some of the things that have changed the landscape. For example, software-defined radio. This is taking or commoditizing radio resources and moving them from dedicated hardware over to software and firmware. Internet protocol. Every use of internet protocol is huge because we're getting away from proprietary protocols that were used before to something that everybody speaks. And there's this thing called control and user plane separation, which will probably be clear later on. But basically what we're doing is we're separating the control and user plane functions and implementing them independently, which allows a lot more flexibility for network design. And also in some cases, it enables things like low latency, which is one of the things that 5G is promising. And then we have software-defined networking, again, taking dedicated hardware, moving it more into software, making your network functions a lot more easily configurable and maintainable. And then lastly, cloud compute. So, your old days of where you had racks and racks of dedicated hardware, like in a data center or something, now can be implemented in Cloud Compute Fabric, which can do things, host things easily, like multi-tenancy and network slices that give you, you can spin up and down resources really fast and really efficiently. So what's our project all about? What are we doing here? To sum it up, we're developing a 5G test infrastructure, basically as cheaply, easily, and quickly as we can. Because we don't have a lot of money, we don't have very much time. We can't go out and buy core, some of the commercial cores out there. So we're trying to do this using open source software and COTS hardware. And we're doing this to explore our different, the effectiveness of our different defense options that we want to test out. So for example, if we get something we want to try, or we have a piece of hardware that we want to test, or a scenario that we want to run, we can really quickly and easily spin up a 5G network and test it and see what the results might be. And so we have some pictures down on the bottom of some of the hardware we're using. Up to the right, the very familiar EDIS V200 radio, and then next to it we have some UEs. Those are IoT devices and a handset, and we're provisioning all our own SIM cards too to work on our network. So each of us, there's 4 of us, including me, on the team. So each of us is running our own core and B and COTS radio. So we call it the D5G stack. It's essentially an LTE stack. So each is running our own stack. So that picture on the far right are 2 of our team members. So they're having a Teams call on Google Meet. And they're each using their own D5G stack. So the one gentleman is sitting in New Zealand. One of our team members sits in New Zealand, and then the other gentleman is sitting on the West Coast. So it's kind of cool. We're using our own network. We're eating our own dog food, as it were. So here's the problem. 5G core can experience attacks from both the RAN side or the data network side. So this purple box is defining what we're looking to essentially defend and also attack. But you might say, okay, in most cases, the network is just like a regular corporate enterprise IT network, right? I mean, why don't you just use techniques to defend that like they do in the enterprise world? And we say, okay, okay, I get it, but you get this radio thing hanging off the side there, and there's like all kinds of IQ going in and out of it, IQ samples, and we have to look at latency, and there's some maybe COM-specific protocols that we have to look at. So defending an enterprise network isn't really quite like defending a 5G network. So we got to figure out, one of the things that we're trying to do is sort of, hey, what are those subtleties that make defenses of a 5G network versus an enterprise network different? So, I mean, that's one of the things we're actually trying to find out. So this is just one strategy we came up with. We're not just looking for vulnerabilities and trying to patch them. We said, okay, let's try and let's look at this holistically from a systems point of view, how we could approach it. So what we did, we're running a red team, blue team. So red team is the attacker, blue team is the defender, and so we came up with ways you can attack the network on the top. So I'm not going to go through all of them, but for example, grant of access. How can basically attacker can get unauthorized access to a network? Destruction and deletion. An attacker could get onto your network and destroy data or parts of your network that could be very damaging. And then along the defense side, obviously you don't have to do anything. And then you have firewalling, which is kind of traditional. There's really nothing interesting about that. I figured, okay, what are some other ways we could use as defenses for our network? So one way is deception, where you are steering an attacker to parts of your network that have little to no value. So if they do something in your network, it's not really going to matter too much. And then one of my favorites is throttling. So that's intentionally making the attacker spend a lot of time achieving their objectives. So you could think maybe you're throttling their network connection down to maybe a few bits per second, where they still have a connection, but it's just getting so frustrating that maybe they move on to something else. So these are all documented on our in our GitHub README. We've defined these pretty well, and you can read more about them there. But so we picked a scenario. We said, hey, okay, we're going to do attack objective. We're going to do grant of access, and we're going to pick deception as our defense response. So what we did was we told the red team, okay, we spun up a network, right? And we told the red team, okay, we want you to access the subscriber database. So that's where all the users are kept, MZs and numbers and all kinds of good stuff. We want you to get in there, and we want you to look for this particular MZ if you can find it, and we want you to do something to it, like add an access point name or change the bandwidth limits or something, just so we know that you altered it. Or if you can't find it, add your own MZ and tell us what it is. And then we also give we give the attacker an entry point, so an assumed compromise, right? We're not making them break into the network. We're saying, okay, here's your starting point. You go do what you have to do to get into this database and achieve the objectives. And so we fire up the network, and then we're not telling them what defense option we're using. So it could be any one of those 6. So we chose to use deception. And so what we did was we said, okay, we're going to spin up a bunch of dummy databases, subscriber databases. So when he gets in there, it'll be a shell game. He might not necessarily know it, or the attacker might not know it, but there'll be a 1 in n chance that that the attacker will get the right database. And so we did that. We ran that. He got in. So the core we're using actually uses a MongoDB database. So there's loads of open source exploits for that. So got in, did that, and it turned out, he got a database, but he didn't get the right one. And he didn't know we're using deception. So he's like, well, if I knew we're using deception, I would have just done them all. And I think we only spun about 6 or something for this exercise. So we're using Dockers. So in theory, we could spin up hundreds or maybe thousands if we had the resources. So changing all of them would not necessarily be an option. But anyway, we learned a lot from that scenario. And what we're going to do next is we're going to do more of these. But it was a really good way to study how other ways we could defend the network. So this is what we started with. This is the network that we started with. It's really simple. We're using open source Evolve Packet Core, open source eNodeB, COTS radio. There's a little picture of it down there on the left-hand side. I think, again, I'm using an Edis B200. All the stuff in the red box is running on the laptop. We are using Docker containers. So I have been asked, what is a Docker container? So if you don't know, real simply, it's a very lightweight VM. So it has everything you need to run applications in it. So we're spinning all these things up in various Docker containers. So we're using this really to figure out how we're going to containerize things and how we're going to orchestrate and manage services, among other things, and how we would maybe approach network slicing. So here's a little detail under the hood from one of our network slices. So you can see there's a lot of different IP addresses there that we have to configure and manage, even for one slice. So we have some open source tools that we use to do this. So in Docker's, I don't know, Docker has its own way of doing networks, and you kind of sort of have to know what you're doing, which I don't. So we have some tools out there that were written by guys. They're actually maintained by 2 of our team members. One's called Dubsnap. So Dubsnap is essentially a Docker network provider that handles all the configuration of your Docker network. So it's basically a command line, and so you can specify all the parameters that you need, and it just makes it happen. It's beautiful. There's another tool called Faucet. Again, also maintained by one of our team members. And Faucet is more, so Faucet really, it takes the virtual and physical networks and it merges them. Again, you're talking SDN stuff. I'm not an SDN guy, but Faucet works with Open Virtual Switch and OpenFlow, and it takes all that and it just makes it happen. I mean, it's amazing. It's magic to me. And it helps us make our networking more consistent. So when we spin these things up and take them down, we know they're gonna be configured the same way every time. So it's really a big help. And this is one example, but when you have several of these, it really does make a difference. So this is our current network, more or less, what we have going today. So as you can see, we've kind of broken out the different network functions. So the colored boxes here indicate how we've broken them out, and we're running them in different containers. So for example, the radio functions are in the green, user plane functions are all in the red, and our control plane functions are in blue. So we're running, so here's what we're running here. We're using Open5GS. Again, it's an open source core EPC. We're using srsRAN as our soft modem. And then we're working with a couple of different radios, NUAN, Blade RX, XA9s and XA4s, EDIS B200s and B210s, and then Lime Microsystems Lime USB radio. And then some of the UEs on the far right there, a bunch of Samsung handsets, and then 2 IoT devices, 6Fab and Blues Wireless. Kind of haven't really got Blues Wireless fully working yet, but we're getting close. So the E node B is for RF. Our G node B, we're not using RF yet. We haven't been able to get the new radio soft modem working with any of our COTS radios. So what we're using is a thing called UE RAN sim. And what that does is it simulates the radio link through an L2 layer. So it's basically just a network connection. Which for what we're doing now it's good enough, but we really want to get to a real RF link there. And so yeah, we do have some 5G core functions are working, not all of them. We're still working on figuring out on how we're going to implement some of them. But we also have, and you can see this in the README. We also have a command line tool that essentially a Python tool that you run it and it sets everything up for you. It asks you some questions and then it'll set up and configure your network for you. You don't have to worry about scripts and you don't have to worry about parameters. It just makes things so much easier. When we started, we didn't have that, so it's been a big help in allowing us to get networks spun up really fast. So just to leave you with a few thoughts here, open source software has really enabled this project. We couldn't have done it without it. So, srsRAN, Open5GS, NextTPC, all of these things. I mean, they've been really fantastic, and they work pretty well for what we want to do. So, I'm hopeful that that community and ecosystem will continue to flourish because it's really, I think, jump-started this project. Another thing, private networks have been kind of an inspiration for us, and private networks are becoming more, prevalent and more attractive because of, you can implement them more cost effectively. They allow you greater control over your network. This is especially true for IoT devices and companies that want to manage their own IoT networks. And then lastly, if it's not obvious, security. So, security needs to be holistically part of your system design from the beginning. Too many times security it's an afterthought, right? It's bolt on, it's not well defined, and left up to the operator to figure out. So, one of the things we're looking at here is how can we make security, how can we think about this holistically for our network before we deploy it. So I think that's everything. So yeah, here's my contact info. We're just getting started, so we'd love to hear from you. If you have use cases or you've got want to collaborate or have ideas, please do give us a shout. Again, there's the repo. And oh yeah, so our labs, we have a bunch. We do a lot of cool projects in labs. I mean, people don't know this because the NickUtel does this, but We got a lot of projects, so you can check out the GitHub on the bottom. There's a lot of cool stuff there. So thank you very much. Can I take any questions?
So I was gonna ask if your testbed is an NSA or SA. It looks like it's a little bit of a mix of both.
Yeah.
But I guess, and I think you spoke a little bit about this, but like, what prevents you from having a full SA? Like, is it just a matter of tooling that doesn't exist, or just getting things that you already have working?
Well, I mean, by definition, we don't have a G node B, right? So we don't have an RF G node B. I mean, it probably looks more like a non-standalone. And we don't have all of the 5G core functions up and running. We have some of them. It might have been not clear. I know it probably wasn't too clear from the diagram. But we only have a handful of the 5G core functions up and running. So technically, it's not really a standalone. But that's what we want to get to, is a full standalone, or at least have that as an option.
Any other questions? No? All right. Thank you so much, Eric.